with example problems. I was having a bit of problem with focus for a moment. So we'll start with problem 30, just part A. We want to determine the resistance and the current through a 75-watt light bulb connected to a proper voltage source of 110 volts. So the push through the circuit is 110 volts, and here's our little problem with voltage, volts, and potential. So voltage is equal to 110 volts. 75 watts is the power required by the light bulb to glow. We want to know resistance and current. So our options are power is equal to current times voltage. This is true whether a device is ohmic or not. So the power required by the light bulb is 75 watts. And the voltage is 110 volts. Oops, I wrote it as 100. Imagine that's 110. So current is equal to 75 divided by 110. Which is equal to 0.6818 amps. And as a check of our units, we have watts divided by volts. A watt is a current times volts, and then we're dividing by volts. So we are left with units of amps. So then we want to know what is the resistance of this light bulb. And in order to find resistance, we're going to have to model it. So P equals IV is always true, whether a device is ohmic or not. When we switch to P equals V squared over R, we're assuming that the device is ohmic. And light bulbs aren't really ohmic, so this is an estimate. So resistance is equal to V squared divided by power, voltage squared of 110 divided by power of 75 watts. So for an estimate for a particular temperature and current, we can estimate the resistance of the light bulb at 161.3 ohms or 161 ohms. You would not be expected to remember that light bulbs are not ohmic. Moving on to problem 20. To slide 20, which is problem 31. An electric car has a battery that can hold 16 kilowatt hours of energy. So kilowatt hours sounds like power, but it's actually energy. 16 kilowatt hours is equal to 6 times 10 to the 7th joules. And so this is energy. It is specifically electrical energy, electrical potential energy. If the battery is designed to operate at 340 volts, so 340 volts is equal to the voltage, a potential difference from one terminal to the other, how many coulombs of charge would need to leave the battery at 340 volts and return to 0 volts? So this is our potential difference. Our idea here is that power is rate of change of energy, so electrical potential energy, divided by time, which we can express as charge times voltage per time. We want to know how many coulombs of charge would need to leave the battery at 340 volts and return to 0. We have a problem of time, of course, but I guess we don't really need to consider power yet. We simply need this relationship, right? We're not worried about time right now. We need to focus in on the idea that electric potential energy is equal to charge times voltage. Voltage is defined as electric potential energy per charge. So if I want to know how many charges I have, I can figure out the electric potential energy and know that the number of charges times energy per charge will be equivalent. So 6 times 10 to the 7th joules of electric potential energy based on the kilowatt hour rating of the battery is equal to the amount of charge available per voltage difference of 340 volts 0 to 340 volts is a voltage difference of 340. So the charge will be equal to 6 times 10 to the 7th joules per 340 volts, remembering that a volt is a joule per charge in coulombs. So I have joules per charge in coulombs. I'm left with charge in coulombs. So my answer is 1.7 times 10 to the 5th coulombs. This is a really large amount of charge. When we were talking about the charge on tapes or the charge on balloons, we had microcoulombs of charge. The charge available to move through a battery or to move through the bank of batteries would probably be more correct in an electric car is enormous. And that's what makes the difference between a 12-volt battery terminal situation for a car versus a 5,000 volt potential for a charged balloon. The danger is not in the voltage, but it's in the available energy that can be transferred due to the battery. So finally, we have problem 32. An electric car uses 45 kilowatts, or uses a 45 kilowatt motor. So the 45 kilowatts here is a rating of the power available by the motor. So this is power, or 160 horsepower, right? I mean, we can convert between watts and horsepowers. If the battery pack is designed for 340 volts, so the voltage is 340, or the voltage difference is 340, what current would the motor need to draw from the battery? Neglect any energy losses in getting energy from the battery to the motor. So energy losses due to the resistance of the wires leading from the battery to the motor. Okay, so we have power, we have voltage, and we want to know current. And so we're back to the relationships between power, current, and voltage. And again, power is equal to the rate of change of energy. But for charges in a circuit, energy is equal to charge times voltage divided by time. And charge per time is equivalent to current. So P equals IV comes from our definition of power and the idea that electric potential energy is equal to charge times voltage, and the definition of current is charge per time. So again, this is based on definitions. This is true whether the device is ohmic or not. So we want to know current, we have power, we have voltage. 45 kilowatts, or 45 times 10 to the third watts per 340 volts gives us a battery or a system current of 130 amps. And again, 1 amp is a coulomb per second. Coulomb is a large amount of charge. So 130 amps is a really outrageous amount of current, deadly amounts of current. If you ever find yourself with an electric car that needs work, everything about the car, all of the information about the car will tell you to not do it yourself. So this concludes current. We'll have a second separate lecture about DC circuits after some in-class examination of current.